Okay, hello and welcome to the Radical STEM Homework Help Livestream. If you have homework questions that you would like answered, you can ask them here in our chat. We will do our best to help you solve them live. In the meantime, I'm just going to be working on some random math problems of my own, but don't feel afraid to interrupt. Feel free to interrupt, in fact. Okay, what should we work on today? Don't think I want to do magnetization. Or circuits. Okay, this one might be fun. Do a little math proof. So let's suppose that A, B, and C are integers. And also A does not equal 0 and B does not equal 0. We want to prove that AX plus BY equals C has integer solutions. Use the shorthand I learned from my teachers. If and only if the greatest common divisor of A and B divides C. That's kind of a lot of that problem statement. So, we're looking at this linear combination, AX plus BY equals C. And we want to look at the greatest common divisor of A and B and see that that actually divides C, and that will make this true, that X and Y are integers. So let's start with the forward case. So we assume that we have integers solutions for X and Y, and then that implies the GCD of A and B will divide C. Then we'll look at the backwards case. So, going forward. We know that there exists X and Y in Z such that AX plus BY is equal to C. So to show that the GCD of A and B is able to divide C, have something divide something else, like P divides Q. That means that P times some other integer M is equal to Q. So we need to show that the GCD of A and B times some other integer is equal to C. Just to save myself on writing, I'm going to let the letter G denote the GCD of A and B. So we want to show that G times some other integer equals C. Okay. So if G is the greatest common divisor of A and B, that means that A equals G times M and B equals G times N for some integers M and N. So we can use that to rewrite this equation. We have G times M plus, times X plus G times N times Y equal to C. So now let's factor out G. So we have G times this quantity being equal to C. But let's note that by closure of the integers, that quantity mx plus, I instinctively wrote b, and y is actually an element of the integers as well. So we have G times some integer equal to C, therefore G divides C. C, not D. Okay, so that's the forwards case. Forward case done. I'm going to write that down there because there's no way we'll be able to fit the other way on here as well. Okay, now the backwards case. Oop. So we're going to assume that G divides C, and then we'll show that this has integer solutions for X and Y. So that is G times, I'm going to use H, is equal to C for some H in Z, for some integer H. Now because G is the greatest common divisor of A and B, we can make the same statements again, that G times M is equal to A, and G times N is equal to B for some M and N in Z. So what can we do with this? Would it help us to solve for G in these equations and get A over M and b over n. I don't think so. I don't think that will help us. We can maybe plug that into here, but that won't get us any closer. So maybe let's just consider this linear combination and see if we can do anything with it. So we have these equalities for a and b, so let's plug those in. G times m plus times x plus g times n times y. And let's factor out g again. M times x plus n times y. Once again, by closure, this is an integer. I believe that might do it. Maybe. So g times some integer h is equal to c. And here we have g times some integer. But we don't necessarily know that h and this linear combination are equal. We don't know that h equals mx plus ny. And I don't know if we can just assert that. Also, this right here, I've just assumed that x and y are integers, which we don't know yet. That's what we're trying to prove. At this point, they could be real numbers or irrational numbers. I guess irrational numbers are real numbers. You know what I mean. I think this is where we're supposed to use the greatest common divisor linear combination theorem. I'm not sure what name it is widely known by. Let me see if I can look it up. GCDLC theorem. I don't quite remember the details of it. Oh, I have found a quite large PDF of notes for a number theory class. GCDLC. Okay, here we go. The greatest common divisor linear combination theorem. For any integers a and b, both of which are not, or where at most one of them is 0, the greatest common divisor of them can be expressed as a linear combination of a and b with integer coefficients. So let's see if I can implement that. I'm gonna step back to before this. So for any integers a and b, we have a and b. Oh, I think that was... okay, it's not that these are both not 0, but... at most one of a and b is 0. So if I had read that condition right from the problem statement, that would be a big indicator that yes, you're supposed to use this theorem. I don't think we actually need this either. So for any integers a and b, not both 0, the greatest common divisor can be expressed as a linear combination of a and b with integer coefficients. So we can say that g equals a m plus bn for some m and n in z. In particular, D is the smallest possible linear combination for A and B. Or G is. I'm going to rewrite that condition earlier, that G H equals C for some H in Z. Let's see. So now, if we multiply this by H, G times H is equal to A MH plus B NH. The left-hand side is C by our assumption that G divides C. And now we can just define X and Y to be whatever is multiplying A and B. So that proves it the other way. We assumed that the GCD of A and B will divide C, and then we found that AX plus BY equals C has integer solutions for X and Y, because these are both I'm gonna write it out as a sentence. Note X and Y are in Z by closure of Z. We got the backwards case done. So that gives us a big QED, a big qued. Okay. That was fun. I haven't done math proofs in a while. Well, I guess that's not totally true. I've done some in my advanced differential equations class, but not rigorous structured proofs, just kind of show that this is true statements. See if I can find some more that I like. Okay, that could be fun. So we want to use congruences. So find the remainder. Want to find the remainder of 2 to the 50th power divided by 7 that's part A. And part B, 41 to the 65th power divided by 7. Let's see if I can remember how to do this using congruences. So we want to find things that are congruent to 1, because then we can sort of drop those from the problem. So we want to think about numbers mod 7 that are congruent to 1. So mod 7, we only have 0 through 6. So what numbers are congruent to 1? We want to find a power of 2 that's congruent to 1. Okay. So find a power of 2 which is congruent to 1 modulo 7. So 2 itself is not congruent to 1, it's congruent to 2 mod 7. 2 to the 3rd power is 8, which mod 7 divided by 7, the remainder of 8 is 1. So if we can break up 2 to the 50 and isolate some multiples of 3, or some 2 to the 3rd powers inside of that, then we can say that all of that piece is congruent to 1 using several theorems, I believe, which I don't remember the details on, but I remember they work. So let's see. 2 to the 50th power. What's the biggest multiple of 3 that goes into 50? 48. That sounds right. 48 divided by 3 is 16. So this is 2 to the 48 times 2 to the 2nd. And 2 to the 48 is really 2 to the 3rd, then to the 16th power, and 2 squared is still hanging out there. So with this, we can say, using some theorem, that 2 to the 3rd, or because 2 to the 3rd is congruent to 1, 2 to the 3rd to the 16 is congruent to 1 to the 16, and 1 to the 16th power is just 1, and we're still mod 7. That should probably be a congruence. So if this whole piece is congruent to 1, then that means 2 to the 3rd to the 16 times 2 squared is congruent to 1 times 2 squared. It's congruent to just 2 squared, which is 4 mod 7. So that is the remainder of 2 to the 50th power when divided by 7. Okay. I'm sure those are some really good theorems if I could remember how they're stated, but I don't. So now for part B, we want to find powers of 41, which are congruent to 1 mod 7. Which will be a lot harder. So 41 itself, mod 7. 7 squared is 49. 7 times 6 is 42. Oh. And 7 times 5 is 35. So 41 itself is congruent to 6 modulo 7, right? Yeah. Because if you divide 42 by 7, or no, divide 41 by 7, you get 0.85, which is the same as 6 divided by 7? Yes, it is. Okay. So can we find a power of 41 that's congruent to 1? I'm just going to look at some powers here. There might be a better, more mathematical way to do this. I'm going to look at 41 to the x, look at it as a table, start at 1, delta is 1. Oh, that doesn't help. What about 41 to the x divided by 7, and we'll look at if it's got decimal places or not. 4 might not. So let's try 41 to the 4th power, and now we'll take that and divide it by 7. Okay, that is not an integer, it just couldn't display all the decimal places. That's probably not the way to do this. I mean, this, we can equivalently say that it's congruent to -1 mod 7, but I don't think that helps us. I don't think things being congruent to -1 gives us the same nice properties as being congruent to +1. I think we'll move on from this one. I got one of them. I'm happy with that. I haven't thought about this number theory stuff in a long time, so some of the details are eluding me. Okay. This might be a doable proof. So prove that M divides A if and only if A is congruent to 0 modulo M. So let's start with the forward case as usual. So if we assume m divides a, then we could use that to say m times, I guess, n equals a for some integer n. Yeah. So can we use that to say that a is congruent to 0 modulo m? Yes. Because now if we look at a over m, that's now the same as saying mn over m, or just n, which by closure, this is an integer. There is no remainder. So I think that by definition should mean that it's congruent to 0. Let me see. The alternate way you can write congruence is that a is equal to m times something else plus what it's congruent to. Oh, okay, so actually immediately from this statement we right away have the congruence. So therefore a is congruent to 0 modulo m, and I think that just proved the other way as well. So we assume that a is congruent to 0 modulo m. Well, that is just another way of saying that a equals m times some integer plus 0, and that is the definition of m dividing a. So big quid. That one was too easy. I'm going to try to find an induction proof. Oh geez, prove the binomial theorem using induction. That one sounds like quite a job. Okay, that one looks interesting. So we want to prove that for if x is greater than 0 for some fixed real x, then 1 plus x to the nth power is greater than 1 plus n times x for all n greater than 2. I suppose that's any real n. No, that would be integer n. For induction it has to be integers. Okay. So for induction, we need to show the basis case for the smallest possible number, and then we need to show that if it's true for one number, it's true for the next one. And those two pieces together will have a domino effect that says it's true for every number greater than that. So first, let's look at the base case when n equals 2. So 1 plus x squared, that's equal to 1 plus x squared plus 2x. Let's compare it to the left or to the right hand side. 1 plus nx, or 2 times x, is, well, 1 plus 2 times x. And if x is greater than 0, then this has to be strictly less than 1 plus 2x plus x squared. Or in other words, it has to be less than 1 plus x, whole thing squared. So it's true for the base case. I'm going to put that up here and then erase to have more room. So 1 plus x squared is greater than 1 plus 2x. Now the induction step. So the induction hypothesis is we're going to assume that 1 plus x to the m is greater than 1 plus mx for some m that is, I believe it can be greater than or equal to. Yeah, it has to be possibly equal to 2 so that it can include what we have from the base case. And now we want to show that this will imply 1 plus x to the m plus 1 power is greater than 1 plus m plus 1 times x. So starting with this, how can we do that? Let's just try multiplying with another one. So 1 plus x to the m times another 1 plus x. And we know this will then be greater than 1 plus m times x multiplied with 1 plus x. Ooh, I don't think that's gonna give us what we want. This will make the left hand side become 1 plus x to the m plus 1 power, but the right hand side will not be what we want. We're gonna get 1, we're gonna get x, we're gonna get mx, and we're gonna get mx squared. We'd have 1 plus x to the m plus 1 greater than 1 plus, if you factor out this x, you do get the m plus 1 times x, but then you also have this. But actually, no, I think that works, because if x is greater than 0, then 1 plus m plus 1 x plus mx squared has to be greater than 1 plus m plus 1 x. So with this and this together, that means that 1 plus x to the m plus 1 power is strictly greater than 1 plus m plus 1 times x. So, therefore, by the principle of mathematical induction, I'm just going to say it's true, it being this statement, for all n greater than or equal to 2. Qued. Nice. I thought that one would be a little trickier. Okay, let's try the divisibility one. We want to prove that 2 to the n plus 1 is divisible by 3. So actually I'm going to write that more succinctly. Prove that 3 divides 2 to the n plus 1 for specifically all odd integers n. Okay. I'm going to try the base case down here so I don't have to erase it and rewrite it. So, base case, the first odd integer would be 1. I suppose this also means positive integers. It wouldn't really make sense for n to be negative, to have negative integers included here, because then you would have like 1 plus a half, which is clearly not divisible by 3. So the base case is n equals 1. So 2 to the 1 plus 1 is equal to 3. And note that 3 divides 3. So the base case is true. Alright, now let's do our inductive hypothesis. We're going to say we assume that 3 divides 2 to the m plus 1 for some odd m, still positive. So we can use our definition of divisibility here to say that if 3 divides this, that means 3 times another integer equals that. So we'll say 3 k equals 2m plus 1. Actually, I'm going to write, before I do that, I'm going to write what we want to show, the condition. So we want to show that 3 divides 2 to the m plus 1 plus 1, or that 3 times some integer j equals 2 to the m plus 1 plus 1. Okay. So we know from our inductive hypothesis that 3 times some integer k equals 2 to the m plus 1. Now can we get to this? So if we multiplied this by 2, we could get 2 to the power m plus 1. And then we would end up with this also being a 2, which is not really what we want. Let's just try that and see what we can do with it. So multiply by 2 and we get 3 times k times 2 equals 2 to the m plus 1 plus 2. Can we work with this? Oh. What if we multiply by I was about to say, what if we multiply by 2 plus 1, but that's just multiplying by 3? It's just weird to write it that way, but that might do something. Let's see. 3 times k times 2 plus 1 equals 2 to the m plus 1 times 2 plus 1. Because we'll still have a 1 on this side, and we'll have a 2 to the m plus 1, and then we'll have some things that we can hopefully subtract to the other side, and maybe still factor out a 3. So that is 2 to the m plus 1 power, and we get a 1. So that's the part that we want to hopefully be able to keep on this side. We also get a 2 and a 2 to the m. 3k times, I'm just going to say another 3. So let's subtract this stuff. We'll get that 3 times k times 3 minus 2 to the m minus 2 is equal to 2 to the m plus 1 plus 1. The question is, can we turn this into 3 times an integer? We have a 2 to the m here. If we can somehow get a plus 1 there, we could say that it's 3 times the thing. Well, we could add a 0. So we could add and subtract 1 at the same time. So 3k times 3 minus 2 minus 2. Oh, also, that's negative. Hold on. minus 1 plus 1 equals 2 to the m plus 1 plus 1. So right here we can factor out that negative and say that this is 3 times k. So 3 times k times 3 minus 2 minus 3 times k plus 1. Negative 2 and plus 1 make negative 1. It's not looking good. Can't really factor a 3 out of a 1. Maybe this is not the right way to work with the inductive hypothesis to do multiplying by 2 plus 1. Maybe, I don't know, this might be crazy. I wonder if simply doing 2 minus 1 would change anything. It might make everything tremendously worse. We'll see. So, oh, I guess that's also known as multiplying by 1. So the left side is still 3k equal to 2 to the m plus 1 plus 2 minus 1 minus 2 to the m. Right, those two talk, those two talk, those two talk. Yeah, okay. So plus 2 and minus 1 combine to make plus 1. So we have the thing we want on the right hand side. Let's add this to the other side. 3k minus 2m equals 2 to the m plus 1 plus 1. By our inductive hypothesis, we could say that 2m is equal to 3k minus 1. This might not work. 3k minus 3k, we get 1 is equal to 2 to the m plus 1 plus 1. That doesn't seem right. Because then if you subtract 1 from both sides, you get 0 equals 2 to the m plus 1, which is simply not true. I think somewhere in here I probably messed up an algebra step. So that is all garbage. Anyway, we're almost at the end of the hour. I don't think I'm going to solve this one before the stream is over, so we'll go ahead and end it there. If you've been out there watching, thank you for tuning in. I hope the next time you will have some homework questions. It's a lot more fun to help solve your homework questions than to work on random ones.